Good afternoon or good morning, depending on where you all are. I'm Josh Cass from Okta. I trust that people can see my screen and hear me. I'll be the first presenter kicking off today. I'm a strategic accounts executive in Minneapolis. I've been with Okta for about 8 years and just want to give you a quick walkthrough of the Okta offerings and how we could potentially support agentic AI. Just a quick safe harbor statement. Some of the capabilities that I'll be mentioning today are well-established, long-standing solutions. Others may be relatively new and are still in the process of being developed. So just wanted to call that out. If there's any questions or concerns about that, we can certainly have individual conversations in the future as warranted and appropriate. With that being said, Okta has two primary platforms. We have the Auth0 platform, which is really built for customer-facing or external-facing applications typically, and it allows you to build agents yourself, help be secure by design. Whereas on the Okta side, we help bring third-party agents and so forth into your environment, into your identity security fabric, and secure them that way. Those are just rules of thumb. That's necessarily completely hard and fast rules, but at the same time, we have two separate offerings and they're both successful in their own right for different reasons. So first, just a quick overview of Auth0. So we offer four key categories when supporting agentic AI. We have user authentication. So agents need to know specifically who I am. So we're not letting this just be kind of a free-for-all, specifically managing who's accessing what. We have a token vault to help with API sprawl and really kind of keep things at a more of a zero trust type of a standpoint, make sure that you've got things checked in and checked out properly. We have async authorization just to prevent the entire RAG pipeline from being accessed. It's specifically what data or what resources can I access or interact with. And then finally, we have fine grain authorization. So this is where we can really granularly fine tune what agents have access to and that they can only access what they need and nothing more. On the Okta pipeline or platform standpoint, this is, I know, a fairly dense slide, but there's really kind of four key areas we help with detect and discover. So we can actually find agents, including rogue agents. We're brought in kind of shadow IT. And we can use our security posture management to identify that, put that into our universal directory. So many people are aware of Okta's universal directory by managing human identities, but we also can manage non-human identities. And then so we can put agents into that universal directory and then kick off governance campaigns and so forth to allow you to apply policies and IT administrative resources to that particular agent. And then on an ongoing kind of post-authentication basis, continually monitor not just human users, but non-human users and agents. So if there are concerns that come up, we can kick off another governance campaign, continually look at access certifications, activity monitoring, including pulling shared signals from other security tools. Technology partners could be like a CrowdStrike, a Zscaler, or Palo Alto, things like that. And then we can also leverage some of the orchestration layer between these different components, whether it be posture management, governance, universal directory, privilege access management, and ongoing threat protection monitoring. So we have really tight integrations, not just with our own products, but also then subsequently integrations with other partner technologies, as I mentioned before, the other security products. And we've also got a very robust library of over 7,000 plus integrations with various applications, cloud apps, the hyperscalers and so forth. So that gives you a very complete security fabric. And again, this allows you to not just manage human identities, which is Okta is probably known for by most of you, but also agents and so forth as well. So that kind of rounds out the overall security fabric provided by Okta. In terms of potential next steps, I would encourage all of you that are attending today to engage with your Fulcrum team and set up a conversation. Could be a whiteboard session, could be a meteor workshop, but kind of walk through where you are with AI in your journey today and look at where you'd like to go next and help get there as quickly and efficiently as possible. So not just the minimal maturity, but getting to more advanced in a set of capabilities, helping you scale and ultimately get to that strategic level as quickly as possible. So really appreciate the opportunity to share some of our capabilities with you today. And again, feel free to reach out to your Fulcrum team. They can engage us and we can have more specific and tailored conversations to align to your AI needs. Thank you all for the time. Appreciate the opportunity to speak today.
Well, thank you, Okta, for sponsoring this session. Today, we're going to talk about using AI for detection. Let me get everything squared up. Okay, so using AI for detection engineering. We want to scale coverage, centralize detections, building a RAG, and keeping the analyst in the loop. So we don't want to automate everything. We want to make sure that analysts can have some feedback. These are going to be some DevOps, some RAGs, and some other automation tools we can use that are somewhat practical implementations used with detection as code. I'm pleased to meet you. I'm Devlin Crooks. I'm a senior consultant with Fulcrum Technology Solutions. I like to bike, I like to automate stuff. I love AI and data, and I also like to automate data, biking, and automate nerding out. So the overview for this presentation is going to go over how we treat alert, noise, and drift, our false positive, fatigue, overtuning, filtering detections, the threshold decay over time, behavioral changes, some context gaps that we can use some semantic reasoning for, detections that lack narratives, mapping, response guidance, creating a centralized plane, scaling and reuse. Redundant detection rules, inconsistent metadata, and annotations often are symptoms that detections have over time when they're just not managed well. There's not a great place to centralize them. And then there's onboarding friction. What detections exist? What gaps do I have? What data sources? How do I respond to my alerts? Where do I start? And the issues that tribal knowledge typically brings over time. So we'll start with the first use case. Ultra simple, but it's pretty amazing. Great place to start. It's natural language to query language. So in this example, I just said, hey, Claude, give me a sigma YAML definition for detecting a lull bit. And right out of the box, it just gave me the title, the ID, status. It's nice and structured to the Sigma syntax. Overview, references, annotations. It's a great starting point. But when you use these, you need to make sure that you follow through with your research, your testing, you validate the scope. And so when you use tools like this to actually develop your rules, you want to make sure you don't just use what it gives you as truth. You want to make sure you define your requirements thoroughly with research and testing. So that's the first part. So whenever we use AI throughout this, we want to make sure that we're always validating what it gives us and we don't take it from an authoritative standpoint. Now, speaking of authoritative standpoints, our knowledge repository, or SNARF if you attended the other talk. So I'm not going to go too much into this, but realistically, this is where we centralize our detection as code, programmatically readable formats for other integrations. So we want our authoritative repo that has all our definitions for detections, response runbooks, testing rules, store runbooks, analytical narratives that explain why we have detections, our query definitions. They're populated with high signal metadata, annotations, MITRE, kill chain, anything else you can think of, any tags. What data sources do they draw from? What required fields do they need? What products are they used in? Their confidence, impact, and risk score using risk attribution. So we don't want to make this into a dumping ground for pasted rules. We want to start small and we want to make quality rules over time. It's also not MITRE bingo. Mappings are informative, not the end goal. So when we're using our annotations, we want to make sure that they have an actual rule. They're not just there to say this covers this tactic. And it's not exhaustive coverage. So we want to make sure that we're growing this over time with data reality and risk rules and other rules that have been tried and tested. So this is the backbone for everything going forward. And you can see on the left and right side some YAML snippets of what a detection rule looks like, in case you missed the other one. So this says programmatic data that other integrations can read from as well. All right, so before we actually start building out the RAG and making a local LLM, we gotta hit the brakes. So when you implement LLMs, that becomes part of your threat surface. Additionally, as you saw before, when I made a detection rule in Claude, we want to make sure that we're not pasting sensitive security data into public LLMs. We don't want to say, hey, I've got Halo firewalls. Give me all the rules I need. And then you say, oh, well, I've also used this product and this product. I use Okta. You don't want to give all of that data because all that telemetry is trained on, and it may resurface in some ways. So treat any prompts like that externally as outbound data. When you build a local LLM or a RAG that consumes stuff like snarf, it's almost becoming a security brain. It's a high-value target. It concentrates detection logic, incident context, and playbooks. So you need to design this as though it were an API exposed to the internet, even if it's segmented internally. Soon, adversaries will try to exfiltrate or subvert it. Designed for containment and monitoring. It's great to have a little prototype, but if you actually mature some of this, you want to make sure you prepare for adversarial tradecraft. MITRE Atlas, NIST, AI risk management frameworks. These are a few sample frameworks you can use to help secure, general guidelines to start securing your local AI space. Now we can do the fun part. Building a RAG. A RAG is a retrieval augmented generation. It's how an AI looks up facts before it speaks. It turns clusters of math into clusters of meaning. When you ask something, it finds the closest cluster and speaks to it. So when we have SNARF as our knowledge base, our analytical stories, our detections, our playbooks, our testing results, they are converted into embeddings, mathematical fingerprints stored in a vector database. When an analyst or an agent asks a question, we turn that query into another vector, and it finds the nearest neighbors, the most semantically relevant pieces of SNARF or the knowledge repo, and it feeds them to the local repo. That result is a context-aware answer, grounded in our authoritative content, not hallucination. So our goal here is to define metadata as granularly as possible, as accurate as possible, to get more solid answers and less hallucinations. So the better data in, the better results we get. We want to be a bit more deterministic in how we structure this. Now we're going to build the backbone. So when I built this, it's on Windows 11, Ubuntu WSL, it's Docker containers, and it is an AI for ants. It's tiny. I use LangChain. Really, it only took 3 or 4 scripts, maybe 100, 200 lines. That includes Quadrant, the Fast API, the Gradio, indexing with LangChain, Ollama, and Postgres. The Docker Compose was 20 lines, very simple. But it's not very secure because it's just running Docker local. Faster optimized models, you don't need to use Ollama for what this is. There's definitely also better embeddings you can use. And if you do try to scale some of this out and you are interested, consider mixed workloads when you're scaling, because it is doing the query, the embeddings, retrieval operations, training, and other inference. I spent about $1 on this. So I used ESCU and Azure Sentinel, and that's anywhere between 7 to 10,000, 7 to 20,000 detections that were consumed and embedded and vectorized. And I did that a few times, about 5 to 10 cents each, using OpenAI's small embeddings. So that's the scope and kind of the testing ground I had going forward. Okay, so now we want to make a RAG with Snarf, or it's almost like a copilot. We want to make sure that we define our metadata and our chunks. So if you're not familiar, chunks are how it looks at data and recalls it inside the vector database. So prose versus code. When we are embedding prose, that's the actual language, we want to make sure that we don't have relationships between the word and the operator and in a query. So we want to make something called a collection, and we want them different. And we want to use words with smaller tokens for good recall, so that we can see, hey, this is where it goes, and it can actually construct the sentences and understand some of the semantic meaning. But if it's too big and you have full sentences, then it's not able to actually find the correct sentences and actually call it back. Inversely, the code, the query language, for example, we want to make sure that operator patterns don't get lost, the functions aren't split across, and you don't have half of your query language cut in half and it just doesn't understand how you're evaling this, for example. And if it's too small, I think I just said that, sorry. What I used is for prose, I used 512 tokens. For my YAML documents, I consumed it as whole chunk, retaining the title, summary, and logic. On the right, you can see how I actually built the metadata. That's typically how I have the parents, the detection, blueprint, tag, tactic, MITRE, data sources. All of that is defined and consumed inside the RAG. And then the code is in a different place with similar embeddings like that, so it can retain that relationship. And we're also using something called a cross-encoder re-ranking. If you're not familiar with what that is, we're going to get the top K results, and then we're going to feed that pair back in and get a relevance score. So when I actually implemented some of this, it was very, very cool. That way we can get semantically close answers. Cross-encoders fix semantically close but contextually wrong results. So if we get a result that is correct, like it fits all our language, but then we re-rank it, it's like, oh, this query is telling me that it wants to detect mimikatz, but it's actually detecting Loban based on some of the event IDs, then we can't do that. That's going to re-rank it and give me a better answer. Trying not to dig too deep into this because it's definitely a rabbit hole. And we're going to kind of touch a little bit based on the technical details, so the actual collections. So we have our snarf detections YAML that we just went over. We have our prose, and then we have our queries code. And then we have our metadata schema. So when we're doing our queries, we are actually going to look at each of these. We're going to have our meta vectors, our logic vectors, our title vectors, top K results. That way we can actually look at how it can actually go through the data, look at the tags, and then make sure it routes, and we can, turn the knobs and weight some of these. And then it puts it all together, gives us an actual answer, gets us the top X results, and then it re-ranks. And I think I don't want to go too deep into this because I don't want to bore you guys. And then I mentioned earlier that we want to start small. So in Snarf or the knowledge repository, where you start is typically 1 or 2, maybe 3 detections. But we want to be able to actually fill the RAG with some data. So when we're looking at using external or imported, we want to consume many public repos to kind of build the context and discovery, but it may be duplicated, misaligned, and noisy. But we want a curated quality. So we'll take a more hybrid approach. In this example, we're taking ESCU, Elasticsearch, Azure Sentinel, or in my case, just ESCU and Azure Sentinel, and we're going to put them into different collections. And we're going to put those weights very low so that it doesn't pollute our other collections, our actual repository that hosts our detections and runbooks that we have that are our data that we want to be curated and authoritative. So the reference data we have here is only used when we want it to be used, and it doesn't pollute our other data. And some other public repositories you can use, Sigma HQ, Panther, Elasticsearch. So you don't just need to use Splunk ESCU and Azure Sentinel, but you do want to go back and make sure that you normalize all the metadata we did before. So annotations, risk score, author, product, log sources. This is basically a way to scale responsibly so that you're not just dumping all the detections and then just causing a lot of chaos, because you'll have some that are public, which may not be correct with some of this metadata, and then you'll have a curated detection that is awesome and amazing, and they're living in the same space, which is not too great. So we built our RAG, and when I built mine, I just said, all right, I want to detect mimikatz. And Mr. Olama said, the detection query for mimikatz is detect mimikatz with PowerShell script block logging, event code 40104. And it referenced the actual detection from the repository. And it even gave me some insight into what gaps it has. And this is just running on my container. So if you have a relatively small, or 16 to 24 gigabytes of RAM for a GPU, it'll cruise, because this is not designed to consume lots of data. It's designed to just intelligently use targeted metadata. So all right, we have our RAG up and going. Now what? So let's move a bit beyond write code for me. So we already saw we can use natural language and public LLMs without actually putting some of our sensitive private data in there. Now we can start using it with detection as code. Let's start at SecDevOps. Detection as code is mature enough to benefit from assistive intelligence, not just code generation. So we'll introduce some practical AI functions that help us maintain detection integrity, context, and governance. And the first one we'll go over is catching meaning drift in detection logic. So over time, you'll have your old logic goes against your testing requirements, your validation, but over time, over months, years, the tuning slowly diverges from its intent. And what we want to do is we want to have embedding comparisons quantify semantic drift the way version control tracks code drift. And so when we have this rule, it no longer aligns with MITRE T1055, for example. It's cutting out some events. And so what we want is the AI system periodically embed detection summaries and field mappings, compare embeddings to detect conceptual diversions, and then alert when logic deviates from its declared intent or MITRE mapping. So if we, over time, keep making commits and it no longer aligns with what we want it to, we actually have some visibility into that. And then let's go to the next piece. Does the rule do what it says it does? Problem. A rule can be syntactically correct but semantically wrong. This moves from static linting to semantic linting. We don't want to just have the AI say, oh, this is how you make the best code. We want to make sure that when it parses our Sigma rule, that it's doing what it says it should do. It's going to parse the SPR Sigma or any other detection code query language. It's going to summarize the detection purpose, go back to its analytical story or blueprint, compare the summary to what it's actually scoping. And oftentimes, if you've tuned it long enough, it's no longer doing what it's supposed to do, or if your management is looking at this rule and you're saying, all right, well, this detection covers this and this and this, but the actual detection logic no longer covers that, you no longer have the mapping that you thought you did. So this is really just making sure that we're bridging what we thought we have our coverage with our actual detection rules. Explaining why detection's behavior changed. So this is another thing that we want to add when it changes. It converts something broke into why it broke. Every day we have our version control changes and we re-index. It enables continuous model governance and drift visibility. So for example, SOC sees the detection actually change, but we don't know why. Why are we seeing this go higher? Well, we can compare embeddings of telemetry context over time. Now this requires some telemetry from other sources that we'll go over and how to ingest those. But it correlates distribution changes with operational events. Plain language drift summaries. Increase in service control manager events correlates with our SSCM agent rollout. So oftentimes when you are looking at your reports and you see, why do we have plus 500 alerts on Tuesday? What happened? And well, some guy rolled out some DB update and set logging to debug, and that inflated all these logs and caused all the baselines to go wonky. This will say, all right, well, why did some of this change? And then we can actually complete a sort of unified assistive loop with semantic drift detection, intent validation, behavioral drift explanation, and then our summarization, our pull request assistant, which you've probably seen in many products that summarize a pull request. This will let you actually see and explain the changes that are happening in your environment over time. So you can actually ask the RAG, what were the most high impact changes? Do we have any risky rules that have been overtuned? Reduces reviewer fatigue. I hate documentation, so I like to automate it. It accelerates code reviews, improves traceability. Like I referenced before, it's almost like a Git copilot for detection engineers. It's really kind of like an LLM-powered dependency management. And you could probably integrate this into CI/CD as an external tool that does not, need to always be there, but is definitely a great tool to have if you have this RAG. And now we're going to start on making some code, and you have your RAG. You want to actually start in developing these detections. Well, a great place to start is just using some gap analysis. We pulled in some public repositories and detections We have those analytical stories, but we don't know where to start. So what we want to do is we want to build a defensible first fast pass map of detection coverage. Note, this is not exhaustive. It's really just designed to scope and identify easy or obvious gaps. So if I have Palo or Okta, what are some good use cases from my data sources that I can use to compile a good detection? It's not going to say, all right, well, here's your entire attack surface. It's really designed to help as a baseline scoping. So I do not use this as a tool that says, well, my RAG said this and this and this. While it may be a security brand that has a bunch of public information in it, it's not going to have things it doesn't know. So if we don't have a detection for it, it's not going to know how to reference it, such as a 0-day. So what we want to do is we want to have our inventory. We want to compare against a data source that we have, the prompt we're feeding it, and then recommend what we can do. We want actionable output, what to add, fix, and why. As an example, in a high-level workflow, the Git is still the source of truth. Our knowledge repository is authoritative. We have a small collection of data sources indexed into the RAG. I won't go too into detail, but this is going to be super small. Our Windows security logs, our Okta system logs, SIM fields, key fields, tags, status. And that's really just good hygiene to know where your data sources are and their status so you can easily reference where they're at. So in case you actually did want to know, all right, am I covered with this? Do I have the Okta logs ingested? What am I doing? And again, the coverage is deterministic. So we want to make sure that we're making this more mathematical than semantic. So we want our coverage and we want to make sure that it requires the sources that are available. So if you have this defined as collecting or planned or blocked or unknown, it's not going to look and say, well, our Windows security logs are blocked, so here's some Windows security use cases. We want to make it a bit more static and deterministic. And we want to make sure the context is tiny. We don't want to make data sources a big part of that, a big part of the vector database. And then here's an example prompt. Snarf coverage copilot. We want to make sure that we retrieve available documentation, available data sources, global, covering these MITRE tactics. And we also want to reference this blueprint. So it can reference any detection that has touched that blueprint. So if you wanted to say, I want to know any detections you have over scattered spider that I can find for Halo or DNS, and it will find any of those detections that you have and then any that you've imported to see what it can populate for you. And that's kind of where it's a good starting point. You can also use public LLMs, but because this is your data, you don't want to expose that or have anything unless you have, strict contract. So this is kind of where the advantage is in having your own AIs. You can put some of your sensitive data in here that you ordinarily wouldn't feed to a public AI. And again, this is not supposed to be totally exhaustive. It's more just a tool to help you scope. The AIs are great tools to help automate and make things faster, but they are not always as accurate as we want them to be. But we are trying to make the most deterministic approach as we can. So hopefully there's minimal hallucinations. When I ran this is kind of where I started to hit some speed bumps. I didn't have enough compute to really get a good output on this. Even though it's there, I can see it trying, it just kept timing out. So a little bit more gas, and this could work pretty easily. The prompts were too big for my container. All right, and now we're going to actually look at how we can use some LLMs inside of detection. So we're not going to go into how we can use AI to consume or not consume our alerts and then say, hey, here's a summary of the alert. Here's our projected, anticipated MITRE techniques that the attacker might use. We're going to try to use something called risk labeling. So we're going to try to merge machine learning, risk attribution, and then semantic reasoning. So this architecture tackles the gap between numeric anomaly detection and human reasoning. It merges quantitative and semantic intelligence. Let's start with how we actually get to meaningful risk scoring. We begin with our raw events. It's a lot of telemetry our detections rely on. Risk-based alerting already condenses these into risk objects and other alerts, but that layer still inherits detection bias and static weighting. So we want to make sure that when we're feeding some of this in the LLM, we're going to make something called a bundle. So these are basically the output of risk events with the risk stripped out. We don't want to taint the LLM from knowing what the risk is. We want it to actually determine what it is. And then we are looking at how do you determine anomalies from machine learning while also retaining some level of semantic reasoning for, say, a malware attack. So we're going to use two brains here. We're going to use an untrained, unsupervised model that uses quantitative deviation that feeds on the output of many of our machine learning rules, as well as any of the risk rules that we have firing. And then we're going to have a pre-trained LLM that interprets semantic intent. And then their outputs are going to be fused together into a single collaborated risk score. High confidence results feed directly into the SIM, while uncertain are retained for analyst review. So we want to make sure the analyst can see some of this and make sure they rubber stamp that this is actually quality and good. We want to make sure that we also feed incident determinations back in so we can remove redundant alerts and also reinforce the learning. To kind of briefly go over this, our bundles are our alerts. So in any machine learning use cases, such as high number of subdomains, unusual number of connections, new ports, novel assets, a user logged into a machine they never logged in before, unusual times. A lot of the heuristics that we want to, in behavior analytics that we want to use and develop are too cost prohibitive. So how do we actually use some of that and develop something that's a little bit of a trade-off? And we do that by targeting some of the machine learning. And before I dig too deep into this, I'm going to kind of give a quick rundown on quantitative versus semantic intelligence, especially when we go into the unsupervised model and how it's basically being an auto embedder, and the pre-trained LLM, which is going to look at the sum of all of the anomalous thresholds and then say, okay, this looks like lateral movement behavior. So for example, quantitative, it's statistical analysis, it's numbers, thresholds, deviations, the meaning, and semantic is the meaning, the intent, and the relationships. So we have a log and count above the baseline, that could be brute force, where semantic is able to see and see that risk, suspicious lateral movement behavior. So model types, isolation forest, semantic, LLMs, embeddings. And the strength of each, precision and math-based anomalies versus contextual understanding. We want to kind of merge these together and weight them differently so that we can have an actual adaptive learning model that has the semantic intent and the quantitative language, our quantitative numbers and rule sets that we fired without overwhelming our compute with just every single bit of telemetry. So that's the main thesis behind this. Now we're going to dig more into the RBA, ML rules, and bundle ingest. So how would you actually construct this? So we want to make sure that we have our risk object that we're attributing risk to. We have a start and end window. Our features are going to be the actual ML values of some of our rule sets. And then our facts is going to be basically all of our risk events that we've seen. So we've seen 11 MFA fails, first seen device. We've seen this NAT fire from our EDR. And these are the data sources that those alerts have fired from. And then we want to enrich that further with any of the other risk information, such as the criticality, the peer group, any other things that exist inside that risk event. We want to make sure we feed to the AI as well inside this bundle. So we want to convert detection evidence into numeric indicators. We want to make sure that we enrich the context, and we want to aggregate this in a bundle, but we want to make sure we strip out the risk score itself. We don't want the anomalous detection to be tainted and say, oh, I can already see the risk score, so I'm just going to inherit yours. We don't want to self-reinforce. We want to find gaps that our risk-based alerting isn't finding already. Okay, so let's actually kind of walk through some of this. Our parallel scoring model. We're going over how we have our detections and our machine learning rules. So we have our statistical analysis. And then we're going to have our unsupervised model learn the patterns from those outputs. And then we're going to have a pre-trained LLM score that's going to learn normal patterns for, oh, that's duplicated. So the pre-trained LLM score is going to use its semantic reasoning to understand the relationship between what those statistical outliers mean. So if any of those are, say, related by MITRE annotations, or if this is brute force, this is lateral movement, we can see that there's something happening. And a lot of the machine learning rules that we fire oftentimes just cause risk bloat and can start firing. So this would be able to determine, we can see some of this, a lot of this benign noise, and we can start to construct a story out of it. And so what each of these parallel scoring does is they make two scores: probability of anomalous and probability of malicious. So that dual scoring gives us measurable probabilities instead of static rule severities. So EDR fires and it's a critical host, we'll have 130 risk score, risk attribution pop. We'll give a bit more insight into that. All right, and then proceeding from those scores, we'll have our fusion and risk label. We want to combine our scores, and it's a real simple algorithm. Our risk is going to be our alpha weight multiplied by our probability of anomalous, and then we have our knob beta for probability of malicious, and our context. So our fusion turns two scores into one calibrated risk. Instead of binary detections, we now have probabilities we can tune and audit. And the analyst reviewed examples, so the system learns what our definition of risky looks like. The risk score, which is an estimate of the total potential harm and negative outcome. So that's just what the actual risk is being defined by the LLM. And then that score is passed over and it's labeled. So our outputs are going to be 0 to 100 or 0 to 1, with 0.87 being an 87. And the risk label thresholds that we also define, so high, uncertain, low, and then our rationale text, which is the context from the semantic reasoning from the LLM. All right, now we want to store and route this. So we want to use OLAP because it's multi-dimensional. We can do full score bundles, so we can replay, backtest, and analyze that. The storage for that can be a little expensive, so we may not feed the whole model back into Splunk or another SIM, for example. But we do want to give it as a stub, a thin record of what it is, and basically an alert that it'll make. Or it won't make in case it was benign or low. And then we have a risk rule routing policy. Depending on the classification and the label, we want to make sure that we make an alert, put it on a watch list potentially, review queue, or low, just archive it. This way we can actually have an audit of what it's done before and replace some of its training if we need to. We want to make sure that the persist scores results efficiently and routed by confidence. We only want lightweight stubs inside the SIM so we don't, again, overload our telemetry. Okay, and now here's where we have the active learning and analyst feedback. So we have the bundles, we have the scores, we have the stubs. We're going to throw our uncertain queue, the ones we're not too sure about, with mid-confidence scores. And we're going to have the analyst look at it. We're going to review the alert that it generated and say, all right, well, I saw this risk object touch these 3 risk objects. And even though they have a risk score in our SIM as like a 40, the rationale is that we're seeing these MITRE tactics that didn't trigger the MITRE story alert, but it is bad. And we're going to label it that this is bad, good job. And we're going to give that a golden label. Now, if it's bad, we're going to tell the LLM that this is wrong, and then we're going to feed it back into the model so that it can learn that this is just benign behavior and don't actually, alert on that. So every decision they make becomes ground truth for the next calibration cycle. Okay, model and calibration updates with governance and monitoring. So this is the final part. This is where we just have our model, and we want to make sure it doesn't drift. It's going to drift, but we really want to control that drift. We want to retrain our numeric models. We want to refine the prompts. We want to recalibrate the fusion weights using new feedback. And then we want to make sure that we log every version so we can explain which model made which decision. Our unsupervised model retraining weekly. We want to make sure that we are updating our prompt guidelines. That way, if we find something anomalous, we can go back and review it. And our alpha beta weights for our probability anomalous and probability malicious, how much we want to weight those. Do we have less confidence in the LLM semantic reasoning? We want to just turn that down some. And then the actual auditing and metrics. So if we wanted to, we could feed this into a dashboard or any other kind of auditable, portal. And so we can actually measure and explain the behavior. That way you can say, hey, this isn't a black box. We know exactly why it's making these decisions, why it decided to calibrate and filter it this way, and why it fired a rule here. That way it's a lot more deterministic, and we can determine, or we can see why it's making some of those decisions. Why did you rate this as suspicious, as malicious, or anomalous? And so we have our detection to decision. Again, this is experimental because I wasn't able to actually get this going on my Docker container. I managed to get the baseline, but what we want to do is we want to have our raw events become bundles. We want to have our bundles become scored risk events. And we want to have our models quantify and interpret, analysts correct and teach. We're going to teach our AI how to ride a bike. And together that turns into a static detection learning system. It's designed to augment risk-based alerting by merging statistical outliers and aggregate anomalies with risk objects, and then enriching them through semantic reasoning. So we don't want to replace or usurp RBA or any other alerting system. We want to make sure we enhance it. And that ends my presentation. Thank you for joining me today. We've explored how SNARF turns static detection content into dynamic, evolving knowledge base. We connect analytical stories, detections, and response artifacts into a single authoritative truth. How we kind of set up a RAG that builds on that foundation, transforming stored knowledge into context-aware assistance for analysts, engineers. And we stepped into risk labeling and how we can actually kind of develop a adaptive learning mechanism and keeping our analysts in the loop. And then finding the biggest detection blind spots or knowledge silos. I'd be happy to continue the discussion after the session, or if you wanted to actually ping me on anything else. Again, thank you very much. My contact information and my company site is in the slide. Thank you again to our sponsors, Okta. Alrighty, do we have any questions?